I request the audience to switch off their mobile phones. So welcome all to this first session of the conference. This will be the keynote address by Professor Udrashta Ramamurthy. He is working as professor at School of Mechanical and Aerospace Engineering, President's Chair in Mechanical and Aerospace Engineering and Material Science and Engineering at Nanyang Technological University, Singapore. He has a wide experience of teaching and research about which we have already heard in the inaugural ceremony. So, without further ado, I request Professor Ramamurthy to deliver the keynote address on the topic of metal additive manufacturing.
Thank you. Good morning, everybody. It's first and foremost, I would like to thank Professor Singh for inviting me to this conference. Can you hear me loud and clear in the back? Okay, very good. Thank you very much. I also want to thank the faculty and the administration of Nirma University for inviting me to this beautiful campus, wonderful hospitality, and this is my second visit to Ahmedabad, actually state of Gujarat, and I'm very impressed, except for the heat, obviously. All right, we have been working. I'm a metallurgist by training, and quite a lot on different kinds of metals I've been working. But for the past decade or so, we started working on additively manufactured metals. And what I will try to do is go through those things. First few slides are mostly introductory. Many of you may have seen it. Please excuse me for those because the idea is this talk is to some extent for the students in the back benches. Metals are arguably the most important materials in the human history. So that is no doubt about it. Why is this case? Why is the case of metals are so important? In fact, this tells you that even our human civilizational development is divided into metals, different ages on the basis of Bronze Age, Iron Age, etc. Right? So, why are metals so important? Because metals are easy to work with. What I mean by work with means you can shape metals into different components, right? Very intricate shapes, like your jewelry that you're wearing, to very large components, for example, a wide-body aircraft, Dreamliner, etc. So, and this, as Indians, those of you, would be very proud that actually Indians are the ones who mastered metallurgy quite well in advance. So, ukku that used to be made in northern Hyderabad, those regions, is wood steel. The steel that used to be exported, and Damascus steel, etc. That used to be very precious, for example. Okay. All right. So metals are very easy to work. You can make all kinds of shapes with them, and they are also tough. That is very important, right? So let me, ask you here, what is the difference between a civil engineer and a mechanical engineer? Both deal with stresses, right? Design of structures, so common things, everything. But civil engineers design structures that are static. They don't, of course, when it comes to earthquake, they may be moving a little bit. But mechanical engineers devise structures that are mobile, cars, aeroplanes, etc., etc. Right? Civil engineers deal with a brittle material, concrete, and they reinforce it just to get some toughness, but mostly in compression, right? So, whereas mechanical engineers can't deal with brittle materials. You need certain amount of toughness because you need damage tolerance. That's why we only deal with metals, mostly metals and alloys. That is the case. Okay. So, so you can also drop them without breaking them. Okay. And this is the conventional manufacturing methods. Rolling, casting, rolling, forging, etc., etc. These are all there. And as a result, metalworking industry is seen, just by looking at the pictures itself, is seen as, somewhat dirty, very noisy, etc. So when I was studying metallurgy, there were no girls in my class because this is not something that, it's not a factory floor that many people would be interested in working on. So in these metalworking processes, there is an additional advantage. So here, this is a super alloy. Can somebody turn these lights off in the front at least, please? So So if you look at it, right, what you have is very inhomogeneous or heterogeneous microstructure. The grain structure you can see, right, very fine here. These are all columnar, etc. So when you do metalworking, right, after you cast the metal, you typically do rolling, forging, thermomechanical processing. You basically homogenize the microstructure. Okay, so this is, for example, a Ti64 alloy, titanium alloy. So in the as-cast structure, you see the microstructure is very coarse. This is 5 millimeters micron bar. So you can have grain sizes that are 2 millimeters, very large. Typically in most of the steels or alloys, you will have in micron length scale, 10 microns, 20 microns, right? 1000 microns is a millimeter. So here you have 2 millimeters. So when you take this as-cast ingot and you do subject them to these kinds of processes, I won't go into those. These are basically, you heat it and then beat it, right? Metallurgy is heat and beat technology, by the way. This is, you've seen, right? Goldsmiths and blacksmiths, they do this, right? Blacksmiths in particular heat the iron to high temperature and make all kinds of shape, heat and beat. So what happens is the microstructure gets homogenized and refined. This is the thing that happens, okay? So now, why am I yapping about microstructures? Because microstructures determine properties, and microstructures, these are albeit a very few examples. The microstructures are vastly they vary quite a lot amongst them. And microstructures determine the mechanical properties, right? So this is the thing that we all really worry about. Okay, so when a mechanical engineer tries to devise something new, right, they all worry about this mechanical performance. So whether this is the most modern vehicle or very old vehicle, or an automobile. So if you there is a Elon Musk in the most, they have this super heavy, they call it, which they want to send it to Mars. So they used actually 304 austenitic stainless steel for the thing. He says you don't need to paint it, and it's a stainless steel, not composites. And there is a beautiful 10-minute video. He explains why. I hope all of you know who Elon Musk is, right? So he explains why the steels are nice, because they want a reusable vehicle, and then it should not fall apart. It should be, composites, if they catch fire, that's the end of the story. So you think that the most advanced vehicles you would want to very advanced composite materials. No, steels are still very nice. Okay, so the microstructures determine the mechanical performance, which is what mechanical engineers do worry about when they design structures, and then the processing determines the microstructure. Okay, so if you understand these connections, right, how microstructure influences mechanical properties, so then somebody from mechanical engineering department, Professor Patel here, comes and says, look, I want to design this beautiful structure. These are the mechanical performance metrics. It should have this much modulus, yield strength, fracture toughness, yada, yada, yada. Then I go back and say, this is the kind of microstructure you want, right? If I want to get this kind of microstructure, what should be the processing steps that I have to take, right? So this is what we spend a lot of time in understanding, okay? And why is it important? Because you change the processing conditions a little bit, right? The microstructure changes, as a result, properties change. So early on, our guest of honor mentioned, right, the CIB to aluminum addition technologies, right? It all looks simple. Even advanced steels, if you want to get, composition is easy to find, but the processing steps are not easy, right? There's small changes that they don't tell you. Recipes are very important, right? Those of you, Professor Patel knows that I'm a foodie. I was talking a lot. So if you're making a nice Gujarati curry, let us say, dish, right? There are ingredients that you have to add at specific times. You just take all the ingredients and put it in one. You'll make a khichdi, but not necessarily a good one, right? So the thing is, there is, even here, metal making, there is a recipe. You need to add at certain times. You need to do the right temperature, right processes, right? So you miss those, you end up with bad properties, bad microstructures as a result. So these are all very, very important, and that's why developing new metals, new alloys which are very important for technological applications, is a very, very time-consuming, costly process. Okay, so now what are the tools that I have in my hand to control the microstructure, right? Naturally that is the thing. So one is composition, right? I add carbon, I add nickel to stabilize austenitic phase in steels, etc., etc. Chromium to increase corrosion resistance, so on and so forth, right? So composition is one, the chemistry of the alloy, right? But that's not the end of it, right? So the processing conditions, how fast you cool. Sometimes we say furnace cool, sometimes we say something else, right? And the thermomechanical parameters. These are all very, very, this is a broad description of what the tools you have, but these are all available to you to tune the microstructure of the material, which will in turn tune the mechanical properties. Okay, now this is all background. Keep that in mind because I'm going to switch over to the additive manufacturing, right? So additive manufacturing is opposite of the subtractive manufacturing that we always use for making components, right? So you make a big casting, you basically roll it, forge it, etc., and then machine it, subtract the material to make the final part, right? So this cartoon will tell you, whereas additive manufacturing, you just take things and put layer by layer to build the 3D structures. So additive manufacturing is a lot closer to nature's way of building materials, components, right? So there are two things that you can already guess the advantages. One is in additive manufacturing, the material loss during manufacturing process is very minimal, right? Here in subtractive, you lose all this additional material. And the other thing is, if you want to make a hollow sphere, conventional manufacturing will not allow you to make it in any way, except for you take two hemispheres that are hollow and weld them together, right? Whereas you can do that in additive manufacturing, right? And so you can build far more complex geometries in additive manufacturing compared to conventional manufacturing. So the design freedom that you have is substantially higher, right? And as I said, nature actually builds in 3D way. This is an example here. Okay, and so as a result of the lot of advantages, especially the design freedom that you have, topology optimization for stiffness, strength, toughness, etc. By minimizing the material that is used, you can actually get quite a lot of advantages, and there are a lot of industries that are interested in it. I am only interested in metal 3D printing. Okay. Now, so what we do is basically build bottom up, right? You are essentially at any given instance, you're dealing with one voxel of a material, if it is a powder based 3D printing, or etc., and you build bottom up, right? That is one important difference between subtractive and additive manufacturing. Okay, and you have to have raw material either in the form of powder or wire. We only deal with powders in my talk. We haven't yet started working on wire arc additive manufacturing. And because metals have high melting points compared to polymers, you also need a heat source to fuse the powders or wires. Okay, so these are the three ingredients. And there is a lot of industry advantage. Okay, so people are already building, so you can actually topologically optimized part like this compared to conventional parts, so you can actually reduce the weight, have a higher stiffness, and like khichdi, this is one pot synthesis, right? One step process, right? It's not necessarily many steps involved. Just that is one major advantage of 3D printing. Okay, and actually 3D printing of metals in particular came from the rapid prototyping technology. So if you, one of you have a new design idea, right? So you want to, it's standard, you make a you design, you make a prototype, test it, improvise, etc. before serial production of that part, right? So prototyping time gets reduced substantially because of the 3D printing. And as a result, you can actually have very quick insertion of new design concepts into service. Okay, so in the powder metal based AM techniques, there is powder bed fusion and directed energy deposition. These are two techniques, and depending on the energy source. In laser, typically is used in DED, so some people call it LDED. Okay. In the case of powder bed fusion, you can either use electron beam or laser beam. So LPBF is a very common laser powder bed fusion is a very common thing that one worries about. So what is the process? You basically spread make a bed of powder, okay, a thin layer of powder, predetermined thickness, and then you take laser or E-beam and fuse it wherever you want, okay. This I think all of you know very well. So what do you need? The inputs are a 3D CAD model, sliced, etc., and then metal powder, and then you have a laser where you can print it. And so I don't think these things are working. In the electron beam technology, what you use instead of laser is E-beam. It's much faster. You have to do it in a vacuum, so you can actually do where cleanliness is very important. Oxidation of the alloys is problematic. So super alloys, for example, are most preferably manufactured using LPBF technique. Okay, so there are each of these techniques have advantages and disadvantages. I am going to skip over this. I think you have video available. You can look at it later. For example, you can get residual free parts because in EPBF typically we heat the base plate. Okay, that is the thing. So you can actually make large parts, but this is much more expensive compared to LPBF technique. Okay, in the laser powder bed fusion, so as I said, so for example, this thing is working. So you actually, a laser scans, and then you deposit a layer, again scans, and you build bottom up one layer after the other, a 3D part. Okay. There are again advantages of all the technique. LPBF, laser powder bed fusion, gives you the highest resolution in terms of specimen feature, or whatever. So you can actually build thin-walled structures. So I was talking to a Boeing executive sometime back. So one thing is, if you have already an engineering component that is being used, right? If you are saying, okay, I have this new production method to make it, it may save me a little bit of weight and replace it. They are not going to do it because still this is still a costly process. So you need to bring additional advantages, right? So you can say, look, I will have a heat exchanger, right? I will build a heat exchanger with this, which will be more efficient, right? For a heat exchanger, if I want to reduce weight, I have to have thinner walls, right? So these are the additional functionalities that you can actually bring in, because you can have very precise, very thin layers of material. So you can have cooling channels very precisely designed and built, things like that. So we'll have so this is one of the advantages of thin wall structures. Of course, it's a very costly, you need a laser beam. That's the disadvantage. In the directed energy deposition, this is a lot more common, simpler thing. What you do is basically you have a CNC machine, instead of the machine tool, you basically put a laser beam. And what happens is coaxially, you can see it here, the laser comes and the powder also comes, and you get, in the flight, the powder melts and gets deposited. Okay. So you have 5 degrees of freedom that is possible with CNC machines. So as a result, you can have much more complicated structures built with this. You can rotate it in the 5 degrees of freedom. So this one allows you to build very large parts. So there are actually some California company which actually builds whole rocket casing in one shot with this technique. Okay. But it's much more coarser, etc., etc. So there are a lot of differences with this technique. So this tells you the 3 different techniques, the advantages. For example, from a residual stress point of view, because you're depositing layer after layer, there is a heat buildup. So there is a residual stress component, significant residual stresses that build up in these things. So from that perspective, electron beam melting technique is much better. If you are looking at low cost, easy to set up, easy to use, high build rates, DED is much better technique, etc. And if you want very complex shapes to be built, the LPBF is better. Okay. So these are kinds of advantages and disadvantages one has in these methods. Okay. Now there is another technique completely different from this. It's called binder jetting. You don't need lasers or E-beams. Okay. Here, what happens is there are companies, Desktop Metal, Hewlett Packard, HP, which is a leader in 2D printing, right? All your printers are mostly made of them, right? They have these technologies. What you do is you make a powder bed, just as a LPBF technique. Instead of a laser, you take some essentially binder, a glue, and you deposit there. So some of you may have, not the young people, the older ones would know inkjet printers, right? Color printing inkjet. So same sort of ink you binder now, print, okay? So you get eventually you get a green part. You then burn the binder out and then sinter it, okay? This is a much cheaper proposition comparatively. And so as of today, in terms of volume, this is much higher compared to all the other techniques put together. Okay, so HP has, we worked with HP on this thing. So I will show you some results later. Okay, now there are a lot of advantages of additive manufacturing. Basically, it allows you flexible manufacturing. You can print a steel part today and aluminum part tomorrow. You can minimize this low inventory cost because you don't need to keep stock of all the parts. This is particularly important for aerospace companies. Of course, you can get near net shape final parts in one step. So there is very little material loss. So this is what they call excellent buy to fly ratio. So if you, for example, titanium is extensively used in aerospace industry, right? So if Boeing buys 100 kilos of titanium, or Rolls-Royce buys 100 kilos of titanium, the final part will not be more than 15 kilos, right? There is a lot of loss of material in machining, in forging, etc., etc., right? So here, if you buy 100 kilos of powder, most likely the flying parts will be also 100 kilos. So this is what is advantage. So this is where some of the cost will be offset. Okay, I already mentioned about rapid prototyping, also functionality, and so this is a myth. Manufacturing cost is still very high, but some of these things offset those things. Now, as a result, that this is digital manufacturing. This is also seen as a fourth industrial revolution, a key part in the fourth industrial revolution. Okay. Now, so there are questions to ask, right? Whenever you come with a new way of manufacturing anything, they will ask these key questions. So first one is benchmarking. Okay. So if I'm saying that, oh, you are already using this part, I want to replace it with a 3D printed part. So you have to say, okay, this part is good compared to this, right? How good the 3D printed part, okay? And the proof is in the pudding, right? How good that is. The second one is there are so many different 3D printing technologies, even for metals, right? So which one is the better one? Is the lowest cost one always the better one, or etc.? Okay. So the final thing is porosity. Now, whenever this is not applied to wire arc additive manufacturing, but powder-based one. So powder metallurgy, we know that anytime you use powders, you always will have porosity, right? Pores, right? These pores are deadly from fatigue perspective. Okay, so if you are going to use a one-off, if it is a rocket that's only once used, it's okay, no problem. But if you are going to use it again and again in a washing machine part, a car part, etc., right? Then the pores will act as crack initiators under fatigue loading. Okay, and then the life of the component will be very low. So structural integrity aspects are big problem for this. In fact, this is still not overcome, right? So as of today, the parts that are 3D printed parts, although there is a lot of investment all over the world, certification is a big problem. Qualification is okay. All the parts are being used are static parts, not rotating parts because of fatigue issues. And of course, there is microstructural design part. I will talk about it later. Okay. Now, I already mentioned this, right? So in conventional manufacturing of metals, right, microstructures are very critical. And for tuning the microstructures, for designing the microstructures, I told you all these three tools that I have: composition, okay, and then I have processing conditions and thermomechanical processing. right? Now, I can still vary the composition for 3D printed parts, but the other two are not there, right? So, this is a major challenge, right? The thing is, I don't have the kind of design freedom, the degrees of freedom available for my designing microstructures, not component. I don't have it, okay? So, this is a challenge, but we have other avenues to tailor the microstructures in these materials. And hopefully I'll show you that. All right, I think Dr. Singh asked me, this is the title of the talk I gave, I will come to it. So now when you 3D print the parts, right, the mechanical properties are very different. Again, the chief guest mentioned about mechanical performance, right? So these are the things that will determine whether a component gets used or not, right? So all these properties are what we need to look at, and I will just go through them very quickly for you. Okay, so the first work when we got in is this. Actually, this is a die-cast alloy, so I hope he was here. So this is aluminum 12 silicon. This is when you add about this much silicon, you get to the eutectic point in the phase diagram. So it's the lowest melting point material. Lower melting point means higher the fluidity, easy to cast. So if you take your car engine or bike engine, most likely it is made of this alloy. Slight variations, magnesium will be there and all that, right? So when we looked at the mechanical properties, we did tensile testing, parallel and perpendicular, etc. What we noticed, so the same alloy, if you take in the cast form, its yield strength is 100 MPa, UTS is 200 MPa, and it has about 10% ductility, right? So this is why it's used. So we take the same alloy, make a powder of it, and then use basically laser powder bed fusion, right? This 3D print the alloy. Okay, so you see that the yield strength has gone up a lot compared to this, more than 100% increase, right? UTS also has gone up a bit, but ductility has come down. Okay, so this material looks now very brittle. So if you take it to a mechanical engineer and say, okay, use this material, they will laugh at you and say, go off, because it's brittle. If you look at it hard, it may fracture, right? So you gain on strength, very substantial reduction in ductility. Okay, we have another variant of this, the slightly less silicon and magnesium, same story. Here we have some ductility, but compared to the same alloy cast, the properties are strength goes up, ductility comes down. Okay, but is it only true for aluminum? No, it's also this is austenitic stainless steel 316L, very widely used. So for example, look at this here. So the green is conventionally manufactured. You see somewhere around 250 is the yield strength. It work hardens a lot and fails at 600. So if this is selectively laser melted or LPBF, you see the yield strength is much higher, even and there is some anisotropy. Okay, so the bottom line is strength goes up, ductility comes down when you take when you do 3D print the alloy compared to conventionally manufactured alloy. Okay, so this is the general observation. Upon laser powder bed fusion, this is the 3D printing technique, but it's also true for other techniques. Strength goes up, ductility decreases. Okay, what is the reason? Right? So what is the microstructural reason? Okay. Now, when you do this thing, metals when they solidify, there is a dendritic solidification that occurs. But here, typically there are rapid solidification conditions that prevail, and this is now deep metallurgy. But what happens is you get these kinds of features. There is a solidification cell structures that come about. Okay. So this is a schematic illustration, and between the misorientation between these cells is very, very small, less than 3 degrees here. Okay, so if you look from the top, you see these cell structures, and from the side you see these are all cells that grow along the thermal gradient. Okay, now this is not just for one alloy. So all the face-centered cubic alloys, steels and aluminum alloys, nickel-based super alloys, etc. All these are face-centered cubic crystal structures. So you see you see these cell structures. They all have it. Okay. So now, depending on the technique you use, the cell scale varies. So here you have 316L stainless steel, austenitic stainless steel. This is also austenitic, same austenitic stainless steel. So the scale here is 2 microns, is 10 microns here. So the average cell size here is 0.63 microns, whereas this one is other additional things. These color maps tell you chemical composition, right? So what you will notice is that chromium, molybdenum, nickel, these are all alloying elements. They segregate to the cell boundaries, okay, etc. This is a super alloy, Inconel 718, which is high temperature super alloy. This is aluminum magnesium that we saw. So all of them have these features, okay. Now, then you do TEM, transmission electron microscopy. You find additional features. So what happens is, it's basically these cell walls. This is a cell. You see, they are all decorated with lots of dislocations. Okay, in this case, we don't have that kind of cell walls, etc. Okay, so there are dislocations that decorate. So conventionally manufactured alloy, let's say you have certain amount of dislocation density, right? Hopefully all of you learned about these defects in materials. Okay, in these 3D printed metals, typically there will be 2 orders of magnitude higher dislocations. Okay, much higher dislocation density. Why does this happen? Right? Okay, so these are schematics of, and there are subtle variations in these cell structures. So in this case, you have only elemental segregation, whereas in the aluminum silicon case, there are actually nanoprecipitates that form along the grain boundaries, along the cell boundaries, etc. So, okay, here you can see that there are precipitates that form. Okay. So why does this happen? So you change the process, it's the same alloy, conventionally manufactured, you get one kind of microstructure, one kind of dislocation density, etc. You change here, right? So what are you doing, right? So you are bringing a laser, and at any instance, what you are doing is you are melting one voxel, not a pixel, volumetric cell, right? You are melting it, right? It solidifies. You're melting next, line by line, line by line. So when you do that, so let's say you scan the next line, this already solidified line material gets heated up and cools down, right? And then you come deposit another layer, right? This layer that is already cooled, solidified, gets heated up, cooled down, right? But it can't expand and contrast on its own freely, like I am moving here, right? So it's constrained by the substrate. It is now stuck to the substrate, right? So it undergoes thermomechanical cycling, some serious thermomechanical cycling. So if you do take the metal, subject it to plastic straining, fatigue, what we call, you get dislocations accumulation, okay? And that is what happens. Those dislocations accumulate around the cell walls, okay? So this is essentially, this simulation tells you that. So there are large amounts of cyclic stress fluctuations, plasticity, and as a result, lots of dislocation activity. So you get large amount of dislocations into the material. Higher the dislocation density, higher will be the strength of the material. Okay, those of you who studied strengthening mechanisms, work hardening. So if you take a piece of metal and you deform it, the strength goes up. Okay, and that is what happens here. Because I'm not working on it purposefully, but the way I'm manufacturing this, there are these changes that happen, and as a result, the material's properties change quite dramatically. Okay. Now, there are lots of debates about this. Some people say this is due to Hall pitch kind of thing, where you have essentially a grain boundary strengthening. So the microstructure length scale changes, now the cell size, that is the reason. And some other people argue that it is because of the dislocation cells are higher dislocation density, then that's what causes the strength. To resolve this, now I'm getting into my own research, quite a lot deep. What we do is we actually could make these micro pillars, okay, not conventional standard tensile tests. So we make these pillars. This is a 2 micron scale bar. So you can see this is a maybe 3 microns in diameter. We go with a focused ion beam, machine it, and we make sure they are all oriented in the same way. And we then can test this as a function of the pillar diameter. Okay. So And then we can look at these properties a lot. So for example, we can make pillars in such a way that there is a cell boundary in this red pillar, whereas this blue pillar doesn't have any cell boundary. So we can actually specifically check out our hypotheses, right? And so we basically see that whether you have a cell boundary or cell boundary free pillar, the responses are similar. That means these cell boundaries are not obstructing my dislocation motion. Okay, so we could do. I can send you the papers, or you can go to my Google Scholar page, and so we published something like 150 papers in the last 5-6 years on this. So I won't go into that will be not Ramayana, Mahabharata, So now when we basically look at aluminum silicon, there are nanoscale precipitates. You can see the cells nicely here, and then we get like bulk rate like response, because here there are precipitates of silicon along the cell boundaries. Okay, and we go into the gory detail of this. Why is it happening? We compare it with let's say nickel that is outside deformed, etc. Okay, I won't go into those details. And so the reason why when you get to smaller sizes, the strength increases because so the dislocations in the material when you deform, what happens is there's something called Frank-Reed source that operates. So this punches out dislocations continuously, right? So dislocations multiply like Indians multiplied after independence. So actually. Sorry, I'm an Indian too, don't take offense. As proud, if not more proud than you. So what happens is, if you take a well-annealed gold piece, right, and hit it with a hammer, the dislocation density goes up inside the material. This is that's what causes work hardening and strengthening, right? So the mechanism is for these kinds of sources keep punching out dislocations. Okay, so now when you have very small diameter specimens, essentially micropillars, so in the free surfaces you don't have. This is what is called a single arm source, and they operate and they cause this strengthening. Okay, that is what happens. But when you go to much larger diameter pillars, the ones inside the full Frank-Reed sources are operational, and they continue. So you get bulk-like response here, whereas much higher strengthening when you have much smaller diameter pillar. So these are the kinds of mechanisms we can explain. Okay, and then we show through TEM what happens, the dislocations cutting through the cell walls and all that. So we do examine this on different things. So here is on DED, directed energy deposited 316L. So there is some silica in this material and it oxidizes. So you see silica particles, those are the particles. But what you need to focus on these traces. These are what we call slip traces. So when dislocations come out of the free surface, you can see them. This is planar slip that is active, and so you see that this. So I hope you can, in the background, you can see the cell walls, right? So all these cells, and these dislocations are cutting through. So what we showed is that. Let me go back a step. So if you study grain boundary strengthening, Hall pitch relationship. This is everybody, mechanical engineers also learn about it. What happens is the grain boundaries, high angle grain boundaries, act as red traffic lights for dislocations. So when dislocations come to a grain boundary, they get arrested. They can't move anymore. That is the reason smaller grain size gives you higher strength. So initially the thinking was that the cell boundaries also act like that, but no. This picture tells you that the dislocations are cutting through the cell boundaries. They may offer resistance, but they don't arrest them. Okay, that is the key difference. So we are able to show these things. Okay, how much time I have?
No.
Okay, all right. This part I will skip. This is going into the further details to show. Now, let me just focus on Ti-64. This is a very important aerospace grade alloy, right? So what happens is, for example, when you fabricate this alloy with particular condition, you get on the top square grains, and on the side these are actually columnar grains. So there is epitaxial growth that occurs, and that's as a result you get columnar grains. But remember, the conditions that prevail are rapid solidification conditions, so you get martensitic structures. So these give very high strength to the material. So for example, if you look at conventional methods, so compared to that, we get high strength. Okay. So again, the same story. When you take a 3D printed part, whether it's Ti-6-4, aluminum alloy, steels, everything, the strength will be higher. Typically, ductility will be lower. Okay. And then we can also heat treat it, change the mechanical properties, etc. So this is the summary about it, right? So what happens is the yield and tensile strengths go up, ductility comes down. The ductility, the strength enhancement is because of the dislocation density being higher, and that's also the reason that why you have lower ductility. Now, it's not enough that you have high strength, right? If you can have a very strong batting lineup, right? But if you have Ajit Agarkar this whole time, that's the weakest link. And then, or look at Afghanistan today. I don't know whether you followed. They were, they played brilliantly. Today they collapsed, right? 56 all out, and they lost. How many of you followed this match? So, okay, yeah, I do all these things. Okay, so what do you say about Afghanistan cricket? It's brittle, right? We used to have this. Indian cricket used to be like this. You wake up, on a fine day, a little late, 1 hour later, it's 60 for 6, and you are disappointed whole day. Very, very pathetic thing. Indian cricket is only for strong-hearted people. It's changed a lot. The 2020 and all these things changed. But now. So brittle, we are very strong batting lineup. We used to have openers Sehwag and Gambhir and VVS and Rahul and Sachin, God himself, I shouldn't forget, right? Ganguly. But then what happens? So strong batting lineup doesn't mean they will last. They are brittle, right? So you take ceramics, they are very strong but brittle. You drop them, they break. So the other important, it's not enough to be strong. See. Sometimes we see some people, right, look like me. I look very strong, right? Our dear friend Singh here also looks very strong. But maybe poke at the right place, we may start crying like a 2-year-old baby. So the important thing is you need also toughness, right? Some people look very thin and whatnot. You beat them or not, they'll not beat them. Don't take my word for that. But they take a lot of, they're very tough, right? So the thing is, for engineering materials also it's very important. It's not just strong is not enough. You have to have toughness. And toughness is resistance to cracking, right? Resistance to cracking. There is a flaw because, any material like humans also will contain flaws, right? It is, no matter what your quality control methods are. So how much is the damage tolerance that material can sustain? That is what fracture toughness, fatigue, crack growth, resistance, etc. tell you, right? So we should evaluate fracture behavior of these 3D printed metals because I already showed you they are strong, right? Okay, so this is, whenever you look at it, at least prima facie, these are the 3 properties that you should look at. Stiffness, this given by Young's modulus, resistance to elastic deformation, strength, tensile strength we already talked about, and toughness. Like, so, when you look at somebody, right, very easy, quickly you describe, right? You look at me and say, he's tall, dark, and bald, not handsome, of course, right? Same way, you say, okay, these are the attributes. There are more detailed attributes that you can think of, fatigue strength, creep resistance, etc. They come later, but these are the primary attributes. And it so happens that any class of material you take, whether you believe in God or not, he or she or whatever, made it such a way that 2 of the properties will be excellent. The third one will be bad. So you take ceramics, they are strong, they are stiff, brittle, right? Metals, pure metals, their stiffness is very good, the toughness is very good, but strength is poor. That's why pure gold, you don't use it. You alloy it with copper. Right? You don't use 24 karat gold, 22 karat, because copper will strengthen the material, increase the hardness, so that your jewelry and all don't wear off very fast. This precious metal, right? That's why you use 22 karat gold. So the thing is, we play with strength and toughness combinations there. So you need to worry about fracture toughness, especially as mechanical engineer, right? So we also work. So there is a conflict, though. This is in old time. There was this nice, beautiful rendition about Saraswati Ma, this morning. Okay, so Lakshmi and Saraswati, they don't, old times, they don't live in the same house, they say, because one is Bahu and one is, Brahma is supposed to be the son of Vishnu, and as a result, Lakshmi's Bahu is Saraswati kind of thing. They don't, well, it's okay. It's just Indian mythological stuff. So toughness and strength go in the opposite directions, right? When you try to enhance the strength, toughness comes down, right? So this is what we think. And so if you go back and remember our 3D printing, what I told you is when you 3D print an alloy, strength goes up. So what do you anticipate? That toughness comes down, right? This is Rob Ritchie actually wrote that, and both are important properties, so you have to optimize. And by the way, this is my academic grandfather, Rob. And I will be tweeting and texting him later about the England India match later this evening. He has been texting me already. The Indian match, So what so the strength goes up. Remember this slide? So when you take the cast alloy 104, right? The strength has gone up, ductility has come down. So that's already an indicator that fracture toughness may be a problem, right? And the cast alloy's fracture toughness is 11 MPa root meters, right? So we were thinking that, this material's fracture toughness will be 1 or 2 MPa root meters, brittle as glass. Glass we don't use we use it for windows and all that, which is not a structural material. You don't make a mechanical device with the glass, right? So that is what we were anticipating. Okay, this is where experimental things are fun. So when we tested proper fracture toughness measurements, so I told you, right, cast alloys fracture toughness is 11 MPa root meters, right? We were expecting it to go to 1 or 2 MPa root meters, but to our surprise, the fracture toughness has gone up. Not, it's not 11 MPa root meters, it's actually gone up, not by 100%, but by 400%. Look at these numbers, right? It's much more anisotropic, but fracture toughness has dramatically gone up, which was a, sort of a very surprising result to us as such, okay? So why does this go up, okay? So go back. See, in conventional manufacturing, it's a top-down approach. You make a bulk, machine things up. Here, like nature, I told you, right? We build bottom-up, right? We build things line by line, layer by layer, right? So and what happens is the way you build the materials gets embedded in the thing, right? So yesterday I had a nice jalebi. The way you make that design will be there inside, how handy or crafted the person who is spreading. So now these are the scanning strategies. So you see, this is a mesostructure I call. Okay, you see how you build. This is one cross section of a laser track. So overlapping laser tracks, and there is a 73-degree rotation. So this gets embedded, okay, in the material. Okay, so what happens is when a crack comes through in this right in these hatch boundaries, there is a silicon that decorates. Okay, silicon is brittle material. What happens is when a crack comes to this, it thinks that, let's say a crack comes to this point, it dives down because there is a lower resistance path, right? Like our students, path of least resistance is what cracks also like. Okay, so when they dive down, right, not knowing how difficult it is to come back up, that is when you have to spend energy. Just let me give you an analogy, right? Let's say you run. I think Professor Naveen ran this morning on campus on a relatively flat land of your campus. You spend, you ran 10 kilometers, you spend say 1,000 calories. The same landscape, but now like this, same 10 kilometers, you started and ended at the same point. If it is very undulated, you would have to spend substantially more energy, right? Maybe 10,000 calories. Right? So the cracks also, when you have a much more tortuous path, you have to spend a lot more energy. Nature knows this, and that's why a lot of structures like our bones, etc., there are a lot of crack deflectors built in, right? So the thing is, when we 3D print the structure, there is this mesoscopic structure which deflects the crack, and you can see it in the fractographs. So there is quite a lot of crack deflection. And that essentially, when they deflects, you have to spend more energy to keep the crack propagating in mode 1 direction, and that's why fracture toughness goes up. So this You remember I talked about the design degrees of freedom that I have with microstructures. So when God closes a door, he opens another window, they say, right? So there were many, not thermomechanical processing is not an option, etc. But mesostructure design, I can change, I can play around with this. I can actually enhance the toughness of the material, right? So this is what happens, when you have a aluminum silicon, you get high fracture toughness and high strength, beating the conventional wisdom. Okay, and we showed this in many other cases. You can see the crack deflections in aluminum, silicon, magnesium, and then so you can actually play around with this as an opportunity to change the length scales in the material, etc. Okay. So for example, here you see that in the DED, if you use fine powder, you don't get, but if you use coarse powder, you can get very distinct mesostructure, and if you use in between, you get. So we have a lot of options about this. You can change the mesostructure as you wish in these materials. Time is it? Okay. There is also fatigue aspect, but I will skip this. So let me go to the end of the slide if you can. Okay. So the porosity is a very big factor, and you have to deal with it. And we also investigate. Yeah, sorry, this is a lot of. Go to the last slide. Yeah, this one, conclusions. All right. So hopefully that I convince you the microstructures of the 3D printed alloys are very distinct, very different from what conventionally manufactured alloys. Same alloy, if it is conventional manufactured, you get on microstructure, 3D print a different microstructure. As a result, they change the mechanical behavior, and you need to understand those before you can really comfortably use them in applications where structural integrity is very critical. Okay, but the thing is, it also gives you new exciting ways to tailor microstructures and manufacture components. So a lot of times people now talk about bespoke microstructures for given applications. So I already also mentioned to you about the things with processing microstructure mechanical performance connections that we worry about. And when it comes to 3D printing, you have also these mesostructures that come about because the way you build metastable structures, I didn't talk about that, and porosity that also affects the fatigue performance, etc. So there are a lot of additional complexities that come, which is good because that keeps us in business. We know how, so that we can do new research and etc. With that, thank you very much for your time and attention.
So I request a member of audience to ask any question here.
Yes.
That's the question. Thank you for your inaugural talk. Yeah. Did heat treatment enhance your ductility?
Yes. Yeah. So in Thai 6.4, we actually did the heat treatment. So we enhanced ductility and fracture toughness as well. I skipped that part. So, the USP, unique selling point of 3D printing is that you make the final part, near net shape part, in one processing step, right? You make it. So some people want to eliminate porosity. Hipping is one thing, but I am not a big fan of hipping. But heat treatment, I argue, is not a bad thing. You need to anyway heat treat for two reasons. One is to eliminate residual stresses. The other one is if you have metastable structures like martensitic alpha prime in Thai 6.4, you need to, many people may not be comfortable with. But in that case, we heat treat it to make it alpha beta. So you just put it in a furnace, right? So it's not really an additional step. Additional step always okay, but not very complicated one. So heat treatment is okay. So we do increase the ductility, but primarily we are using it for enhancing fracture toughness. Yes, ma'am.
Sir, the DED technology, if we compare it with the of 3D printers, do we see the same behavior?
No, it's very different. So the DED, so in laser powder bed fusion, we use finer powders. Layer thicknesses are much smaller. In DED, the layer thicknesses are much coarser. You use coarser powder, much coarser also. As a result, the microstructures are different. For example, in 316L, dislocation density is somewhere between an LPBF alloy and a conventionally manufactured alloy. So the properties are different. So that is why there is no one answer to everything. So if you, for example, if you take one alloy, one method, you get one kind of properties. You have to study. Unfortunately, there is no generalization. Yeah. Yes.
Does the initial microstructure plays a role in deciding the final properties? Because, like for example, everything hypothetic or hypothetic, you take the
Yeah. There is so unless really you take it to very high temperature, there is some that memory kinds of things. In fact, we have a paper titled "Cascading of this." So even if you heat treat in a Inconel 718, which is actually you have to heat treat because you have to age it. So there is the cascading of that microstructure. So the way you built it, that memory is there. All right, it's not going to go away. So unless you sort of almost take it to very high temperatures and whatnot. Yeah.
I have one more question. Is the microstructure organized around the thickness of the part?
Yes.
Layer by layer.
Yeah.
So when we are doing the microstructural study, from where we are taking the segment?
So we make sure that it is not the case, but some parts what happens is from the bottom to top, there is a significant variations in microstructure. So, but because essentially what happens is the heat gets built up. It's not all dissipated. So, progressively as the heat builds up, in the thing, there is a microstructural variation. You need to worry about it. So, this is another important reason why I think 3D printed parts are not extensively used, because there is a certain expectation from end user. If I bought a piece of material yesterday and 5 years later, I want same consistency, right? But there is some variability, from machine to machine variability, day to day variability, etc. And that is something that we have to get a good handle on. Even there is spatial variability, as what you are talking about. In our studies, we make sure that we are okay with that. Yeah. Yes, sir.
So how does the size of the metal product, size of the metal product affect the mechanical performance of the additive manufactured product?
So the size of there is an intermediate step. So what happened is size of the powder affects the microstructure, and then microstructure affects the part. Right? So in fact, I quickly showed coarse powder and fine powder, right? I get the very different microstructures there. So and this sometimes what happens is there is the columnar grain growth that occurs in most of these things. So if you have coarser powder, you could get more equiax structures and all that. So there is powder size effect very definitely. Right. In fact, we have a nature comm in this very aspect on 3169. Yes, somebody from there. Yes.
So, given the same parameters in the same process, is porosity predictable? Is it consistent?
It's consistent. Predictability is still, not gone to the stage where we can really predict the porosity. Porosity though is inevitable in these materials. So, where we can minimize the porosity but not completely eliminate it. Predictable, not there yet. If you can predict, then you can always find ways to eliminate it. Yeah. All right. With that, thank you. Thank you very much again.
Thank you, sir, for the knowledge presentation. Actually, I can relate to the analogy which you gave. I teach this basic course of material science to semester 3 students here. So I give the same analogy that don't be very strong on it, because if you are very strong, that means your hardness is very high, and hardness is surface property. So at the core you will be not so strong, because the toughness will be low. So you should be tough and hard and strong at the same.
Yes.
Not on.
Unflexible.
So I can So thank you for this session. Now I request Dr. K. Patel sir to felicitate Dr. Professor Ramamurthy. Okay, now it is time to hear from Professor S. Ravi. She is Professor of Mechanical Engineering and